Welcome to this video tutorial on how to complete 11700 top intersect. We're also going to cover GDT on parallelism, perpendicularity, and angularity. Now, unfortunately, my SolidWorks license is not currently working, so I can't make the blueprint. But this is a simple enough part that we'll be able to just call it out by eye, and you will be able to look at the blueprint on Blackboard by the time you look at this. So we'll start with the CAD file. We'll go CAD file, load, we'll grab the CAD cube and say open, and then we'll turn on our shading. All right, so for this one, we will just place our CAD model directly onto our table. No need to orient it in any way. So let's display our table, our base plate, and go fit, and then we'll come into CAD model modification. And we'll say center. We have drag base alignment turned on. Basically, we want that on if we're not going to reorient the model. And then we'll click on position. We'll click right on the bottom of the model. We'll click right on the top of the base plate. And we'll hit apply and close. And then we'll go to an isometric view and fit. And we could turn our base plate off because we're now in the correct location. All right, so first thing we're going to start with is our standard 3-2-1 alignment, and then we're going to check the parallelism of this surface down here to this surface up here. We're also going to check the perpendicularity of this surface over here to this surface up here. And then we're going to check the angularity of this surface over here to this surface up here. And now that we're starting to do GD&T, or geometric dimensioning and tolerancing toolpaths, we're going to start using scanning instead of just regular touch points. Now with that said, for your alignment features, it's still faster and easier to use regular touch points, so we'll use regular touch points for our alignment. One other thing I'd like to add to this video is, how do you do intersects? How would you create a line out of the intersection of this plane and this plane? Now, of course, the CAD model does have that line on it already, but if we're trying to replicate that in our point cloud, how do you do that? So I'm just going to make up a tolerance here, and I'm going to say I want to know the two-dimensional distance in between this edge here and this edge here. And I want to know that as I'm moving my mouse here. I want to know the hypotenuse of the triangle. I don't want to know the x distance. I don't want to know the z distance. I want to know the two-dimensional distance as seen from this view. So we'll cover that in this video as well. Again, I apologize for not having the blueprint, but what I just mentioned is what we're going to go over. So let's start with our base alignment. And actually, let me back up a second. I just happen to notice that we have the 1.5 by 31 millimeter probe on this. And based on what we're going to be measuring, based on what I just described, there's no reason that we can't use our standard 3 by 50 millimeter probe. So the first thing I'm going to do is change that probe. So I'll start by, I guess it's good practice to just move the probe out of the way so we don't crash into anything on our way. Yes, I know it doesn't matter. It's a simulation, but it is a best practice thing. So we move our probe out of the way. Again, we can't use the automatic tool change. It's not configured, but we can use manual. So we'll go manual, pick up system, OK, come down to the 3 by 50 and say OK, and then close. And now we have our 3 by 50 millimeter probe. So now we'll start our base alignment. This is going to be the same as we've done in the past. So if you have a template you want to start with for this, that's just fine. You can start with the template. In my opinion, it's just as fast almost to just recreate it. All right, so there's our base alignment, and then we'll come down to clearance plane from CAD model, and OK, and always say no to that update clearance plane dialog. And then we'll come back and just make sure that the strategy that's used to do this makes sense. Well, it looks like the default strategy that I've configured for planes happens to be a polyline. And we are actually going to talk about polylines in this video, but that is not what we want for our alignment. We want 1, 2, 3 points on the top plane. And then for our 2D line, we'll get rid of whatever strategy is in there. It looks like it's an auto scan path in my case. It might be something different on your computer, depending on what defaults you have set. And the point already came in with its strategy. Maybe we want to grab these and just form a group, and then we'll rename the group alignment or align or something like that. And that way everything will stay organized. All right, so I said one of the things that we want to check is we want to check the parallelism of this slot to this top surface here. All right, so this top surface is going to be the primary datum. So to do that, I'm going to need to have this surface here. We're going to check the perpendicularity of this surface to this surface. We're also going to check the angularity of this surface to this surface. So first things first, we did an alignment, but we don't have a great idea of where this surface is. We just touched 1, 2, 3 points. I really want to have a much better idea of what's going on here. So I'm going to hit Define Select Geometry, but wait, it only gives me the existing plane that is already there. So Define Select Geometry will only pull each feature once. What I have to do in this case is I want a duplicate plane. I can either copy paste this, or I could go Extract Features. And now notice how that gives me a duplicate plane, and it puts that in the group. I'll just pull that outside the group. All right, so now I have a duplicate plane up here. I know I'm also going to need to measure this plane down here, and this plane over here, and this plane over here. And if I had Define Select Geometry already selected, then when I click on it, well, let's try it. When I click on this, it will simply highlight that point because I've already done something on this feature. It's already extracted that feature. So when you say extract features, it will allow you to do duplicates. So that is something that seemed kind of strange to me, but you get used to it. So with plane 2, notice that my default strategy, I'll click on strategy here, is a polyline. Well, if yours didn't happen to be a polyline, let's just get rid of it and recreate it. It's actually extremely easy. So we'll click on polyline, and then we'll double click on that. All right, for now, I'm going to skip all the way to the bottom, and I'm going to say polyline from model. And for my edge distance, usually anywhere from 50 to 100 thousandths of an inch is fine. So in this case, let's go with 75 thousandths and see how that looks. All right, and the reason I went with kind of a small value there, you see how close we get to this circle? I don't like how close it is to that circle. Notice that it just grabs the exterior edges of this surface. This isn't going to work for us, so I'll just hit all the delete button on all the points there. And then I'll click polyline from model again, and instead of 75 thousandths, in this case I'll try 50 thousandths and say OK. And there we go, it drops the polyline on the model. Beautiful. We'll come back up to the top here, and based on the size of this feature, I'm going to set the speed to 0.5. I don't even know what units that is, to be honest with you, but 1 is fast and 0 is slow. So anywhere between 0 and 1 is a good number. For smaller features, go smaller. For bigger features, go bigger. What's a good value for this? I don't know. Why don't you give it a try? Try anything between 0 and 1. And if you're not getting repeatable results, that's too fast. If it's taking too long, well, I guess that's either too slow or you're just going to have to live with it. So as far as our step width goes, usually 5 thousandths of an inch is good unless you have an extreme precision application. The smaller you set this step width, the more data you get. More data is not necessarily better all the time because it can bog the computer down or cause your sensor to quote-unquote miss readings. So if you keep missing readings and having to repeat the measurement, that's not fun. Then you would want to open this value up a little bit bigger or slow this value down a little bit smaller. These settings seem to be good for a plane about this size. We'll say OK here, and our polyline is done. Now you might ask, hey, how come we're not measuring that polyline just as part of our alignment feature? Well, you got to figure with your alignment feature, you really don't know exactly where the part is. The alignment feature is meant to get a rough idea of where the part is. It ends up being pretty precise, but not precise enough for many GD&T tolerances. Keep in mind, every regular rectangular tolerance has some degree of GD&T built into it. So if you're using a GD&T tolerance, that's going to be tighter than the existing rectangular dimensions that are already on the print. So a lot of times GD&T by definition is just a tighter tolerance than other tolerances. It makes sense to scan when you have tight tolerances. All right, so we scanned for plane 2. Let's come into plane 3 and let's look at our strategy there. Let's get rid of whatever's already in there, and then we'll make a polyline. We'll double click on it. This time, I don't know, I guess we'll work top to bottom. So we'll set our speed. This is a much smaller surface, so I'll go 0.25. Step width, we'll still go with 5 thousandths. And then we'll click polyline from model. And for our edge distance here, well, it looks like we got to fit our 3 millimeter probe inside of there. So let's go with something more like, let's go with 100 thousandths and see how that looks. Yeah, and it looks like that offsets it pretty nicely. You got to keep in mind this slot might be installed at a slightly different angle. Maybe this CAD model is not perfect, so I'm giving myself some amount of offset for that, knowing that I don't want to ram the side of this stylus into these walls here and here. All right, so everything is looking good here. We'll say OK and OK and OK, and then we'll come right back to plane number 4. We'll go strategy. There's an existing polyline in here. I'm just going to delete it so I can show you how to recreate it. We'll go polyline, double click. On this one, I'm going to use a measurement speed of 0.5. Step width, 5 thousandths is usually pretty good. Polyline from model. Edge distance, here we'll go with, yeah, sure, 100 thousandths should be fine. And we'll say OK. All right, now I'm not concerned with any of the planes that we've measured up until now, because they have plenty of clearance. But when we look at the length of this probe, and let's actually just jog this probe over a little bit in our base alignment coordinates. Let's jog this to maybe x of minus 100 thousandths, and a y of 0, and then a z of, minus a half inch just to start. Whoops, minus 0.1. Okay, I guess it doesn't want to let me put minus decimals in there, I guess. It's interesting. All right, so when we move this probe into location, we notice that if we try to measure all the way down to the bottom of the surface, look, our probe, our entire stylus system and the sensor itself is really close to hitting the part. So I really don't want to do that on STCC's machine. So we'll just have to be mindful of this as we come into our last plane strategy, plane 5. Notice that the default strategy that I have of polyline will actually cause a crash here. If we drag this all the way along, you see the bottom line here is below what the probe can reach. So when I do this polyline, I'll still do it the same way as I did before. I'll go polyline. We'll go with, this is a good size surface, so we'll go with 0.5 on our measurement speed, 0.005 for our step width. And then we'll go polyline from model. And with our edge distance here, 100 thousandths is probably fine for a larger plane like this, but I don't like how low those bottom points are. So what I can do here is click on Show All Points, and I can just grab these lower points and just pull them up. I'll just pull them up a little bit. And now our polyline is not nearly as deep. So you want to pull those up to the point where they're about halfway down that surface, and then say OK and OK. So this is one I'm definitely going to be looking for when I check your labs. I'm going to remove a significant amount of points if I see that you do not edit this surface. So just fair warning. I don't take this one lightly because this runs the risk of crashing the machine. You really have to be aware of what you're doing in this case. All right, let's just get our probe out of there just for best practice. Okay, so now we have pretty much everything we need. The one thing that we don't have, we need to measure the hypotenuse of this angle right here. So we're going to need to construct some features. This is the first time we've used the construction menu, and a lot of these are pretty self-explanatory. So I recommend you just play around with them. Let's try intersection for this one. So with intersection, I want to know where this edge is and where this edge is. So it's going to take two separate intersections. The first one is going to be the intersection of whatever plane this is and whatever plane that is. So let's find feature 1 is going to be plane 5. And feature 2, in this case, is going to be plane 4. And notice how that highlights the edge on the screen when we do that. And we could intersect a third feature, like if we intersected this plane over here, we would get a point. All right, let's copy paste that intersection. And this time we're going to intersect plane 4 with plane 2. And that gives us that top edge there, and we say OK. So one of the tolerances, again, I apologize for not having a blueprint, but one of the tolerances is the 2D distance from here to here. Now, I'm going to do this wrong first to show you why we need to measure this front plane. So let's come over to size and distance, and we're going to come to polar caliper distance. And then we'll double click on that, and we want the distance between intersection 1 and intersection 2. And notice that it's waiting for a primary datum here, and we don't have a primary datum. So the way I explain a primary datum is if you picked up a pair of dial calipers and set them down on a surface plate, what surface do you sit them on? Well, that's your primary datum. And for this measurement, we really want the one of the caliper edges to be right here, and another one to be right here. And we want the dial face of the caliper to be here. Right? And we want the rack and pinion assembly of the caliper to be facing that way. Well, if we were to set this down on a surface right now, we'd be setting it on this surface. This is our primary datum. So if we try to do this and say OK, at this point we can come over to our Features tab, and we can, well, actually, this is a good application where we could, I don't really care about the path right now. I just want to see if this feature works. I'll go Run, and I'll say All Characteristics, and I'll clear the results, and I'll set this to 55, and I'll set some other stuff here, and I'll hit Start. And now you can see where those scan paths can be really painful. They could take quite a while to run. Notice that I'm running my speed all the way up. If you slow your speed all the way down, these scan paths are very, very painful. So that's why we've been using single points up until now. I'd say you really don't want to use a scan path unless you have to. If you can do it a simpler way, do it a simpler way. Single points are almost always simpler than scan paths. Whoa, look at that clearance there, right? It shows you why we had to modify that that polyline for that particular feature. All right, so our report is generating in the background, and it tells you features concerned, polar distance 1. We get a dimension report here, and the dimension report says, basically, you can't output that feature. I'm not even going to try here, right? It says polar caliper distance 1, error with references. So what is the problem here? Well, the problem is we actually don't have a plane on the front to use as a reference. Now, we certainly could scan this front plane, but again, if you can do it a simpler way, do it a simpler way. If we say define select geometry, in this case, when we click on the plane, it's simply going to bring us back to the 2D line. So what we want to do instead is go extract features, and we're going to extract this plane. We'll double click on that plane, we'll come into our strategy and get rid of whatever might be there. And in this case, we really only need 3 points. So 1, 2, 3, I'm being careful not to go deeper than the length that we have on our stylus. That is certainly something that I was not paying attention to when I was new with the software, and then you go to run it on the machine, and whoa, that gets way too close. All right, we'll come back to our polar caliper distance, and for our primary datum, we'll set that as plane 6, and notice that it gives us an actual value here. So in most cases when you're creating tolerances, if you don't have an actual, you probably did something wrong. All right, so we learned how to do intersects. We learned how to do the 2D distance on some funky plane that is not on one of the standard Cartesian planes. Now we want to come in and do some of our GD&T callouts. So we need to know the parallelism between the bottom of this slot and the top of this plane. So here we'll come to form and location, and you might as well call this the GD&T dropdown, right? We'll come down here to parallelism, and we do have to be careful with the order that we select this in. So for parallelism on this particular feature, yes, we don't have the blueprint, but when we do, the shape of the zone will be 2/1000ths. All right, there's no MMC modifier or anything like that in this case. We'll go for feature, and the feature is going to be the feature itself, which is going to be the bottom plane. It's going to be, it's whatever is not your datum. And of course, our datum here, when you see the print, this will be datum A, this will be datum B, and this will be datum C over here. So we need to compare our parallelism to datum A only. So we have to do the primary datum. We have the option of doing the secondary datum. In this case, we're going to do the primary datum only. And that primary datum, it could be plane 1, but we have a much more precise representation of where plane 2 is because we scanned it. So I'm going to select plane 2 in this case. All right, and we'll say OK here. And notice that that didn't give me an actual. Well, I think that might just be the fact that we still have some gray over here in our features list. So we could come over here and just hit run, and we could run all characteristics. And I'm not even going to clear the existing results this time. I'm just going to hit start. And I think the reason that one didn't output is because we hadn't actually measured that lower plane there. Hey, perfect. There we go. So now we get a parallelism value, and in my case, it's 4 thousandths. Now when you do this on your computer, this may actually give you an answer of 0, and it doesn't mean you're wrong if you get an answer of 0. The reason, let's get rid of this one. The reason why that's giving me something different is because I went up here to Extras, Settings, and Measurement, and I came down here to, Simulation, the Simulation tab, and I turned on Active Dispersion. And this is going to make it look like your CAD model has errors in it, when truly it does not have errors in it. So I set my Active Dispersion from 0 to 5 thousandths. Well, I'm going to tighten that up a little bit. I'll set it from 0 to 2 thousandths. Actually, let's set it from 5 tenths to 2 thousandths. And then for a constant displacement, I just did 1 thou, 2 thou, and 3 thou, just to have some values in there. And now if we run this again, this time I will clear the existing results. Now we're going to have to wait for the scan path. The reason I cleared the existing results is if I didn't clear the existing results, we would have the old results, quote unquote, stuck in there, and we'd get ultimately the same result. Now we have new dispersion settings, so that is essentially the same thing as taking off one part and putting on a different part. So we are only scanning the features that are required based on the characteristics that we wanted. So if I had thought about this, I would have selected parallelism 1 only, just to show you what I'm trying to show you here. That way we wouldn't have to wait for these additional planes to scan. But hey, hindsight's 20/20. All right, so that's looking good. Oh, yep, it had to measure that plane on the front as well because it needed that for that caliper distance. And aha, notice that the parallelism is now at 1 thou and 5 tenths. So that is active dispersion. If we turn active dispersion off, this value and any GD&T values for that matter would come in at 0. So use dispersion if you think it's helpful. Don't use it if you think it's not helpful. Now, one reason I really like dispersion is if we double-click on parallelism 1 and we click on PyWeb Reporting Plot View and we click Plot, notice that this gives us a graph of exactly what that surface looks like. And the shape of this surface, by the way, is the shape of that slot that we measured. You can even see the radius that it followed. The polyline automatically puts a radius in there. You can actually see how that kind of fits in. The slot's at a slight angle. This plot is also at a slight angle, right? So you can actually even get these visual plots to print out as part of your dimension report if your part requires it as well. For right now, we're just going to look at them to satisfy your curiosity. We only have a couple of them. No need to waste extra paper or extra gigabytes putting them in your PDFs that you're submitting to Blackboard. But yeah, if you want to look at them, you just double-click on the GD&T tolerance itself. You come into PyWeb Reporting and hit Plot. And so this data is made-up data. This is the active dispersion here. If we come in and turn our active dispersion off, which I'll do now, I don't believe that will retroactively change that, but it should change it for future features that we measure. So let's just turn this off entirely and hit OK. And now we're going to come in and output the perpendicularity of this surface to this surface. So when I say to this surface, that means this surface up here, plane 2, is going to be our primary datum. So it's a GD&T callout, so we'll come up to form and location, we'll come up to perpendicularity, and our feature is the one that we want to measure, which is plane 5. And our primary datum is going to be plane 2 in this case. We'll say OK. Shape of the zone. With this one, it's a bigger plane, so we're going to be perpendicular within 5 thousandths. Notice it is giving me an actual already, so I'll say OK here. Now that's interesting that it gave me an actual and it put in a number here, and that's because I have already measured this plane. The actual is at 1 thou and 5 tenths. So if I want to update that with my not having dispersion now, right? You can see there's the dispersion in action again. You can see the peaks and valleys don't look quite as extreme because this is a much larger surface here than the other one we looked at over here, right? So if I want to rerun this and get my actual down to 0, you know what I'd have to do? I'd have to hit, notice I have perpendicularity 1 selected only. I hit run. I am going to clear my existing results, but I'm only going to do my current selection. And now I'll hit start. And in theory, if I'm right, then we should only scan the top surface and the surface on the left side because that's what we set up in our run window. So I know in the beginning of this class, you know, when you're new to Calypso, that run window can be very daunting and confusing. Now that we're using a little bit more of the functionality, I think it's probably becoming a little bit more clear why they have all those different options, right? In that case, it did exactly what we expected it to do. And notice that our measured value is now set to 0. So we also covered how to do dispersion. Notice that when I cleared the existing results, these other two characteristics that we already had a point cloud for, they went away because this clear existing results is an all or nothing. It either destroys the entire point cloud or it does not. Right, so in that case, I did clear existing results because I wanted to force whatever measurements we had of this perpendicularity out of there so I could get them back in with no dispersion, just to show you how that works. All right, the last thing we have here is the angularity of this angled plane to this plane up here, and I think we're going to need a secondary datum on this one, and I think that secondary datum is going to be this guy over here. So we'll go form in location, we'll go angularity, and for, yes, exactly. Notice how our secondary datum does not have a red X in it. We do need a secondary datum in this case. Now our tolerance on this one is going to be 3 thousandths. Our nominal angle, I believe, will populate itself as soon as we give it some more information. So the plane that we're trying to output is plane 4. Our primary datum, this is what, if you were to draw the angle symbol, you would pull off of this line and this line. So the primary datum is the first line, and the measured feature is the second line. The secondary datum is going to be this front surface because that is the plane that you drew these angles on. All right, so our primary datum is going to be plane 2 in this case, so we'll say OK, and our secondary datum is going to be plane 6 and OK. Notice that that picked up our nominal angle of 40 degrees, and we say OK. However, we don't have anything in our angularity here, and that is because I destroyed the point cloud. So let's, in this case, let's just hit run. I'm not going to clear the existing results. I'll do current selection, which is only angularity 1, and we'll hit start. And we're only going to measure this plane here and this plane here because we already have the top plane as part of our point cloud. So we don't need to measure it if we already have it. All right, beautiful. And our angularity, our measured value is 0 and our nominal value is 0. And you might say, hey, that's strange. Our nominal value, it even said our nominal value should be 40. Well, when you're working with GD&T callouts, your nominal value is set in the characteristic itself. Like for parallelism, our nominal value is 0, right? Two planes have to be parallel, 0 degrees off. We didn't even have to enter that one because parallelism is really like angularity, or it's a special case of angularity where the angle is known to be 0. In perpendicularity, same deal. That's really angularity where the angle is known to be 90. And those didn't show nominal values either. So why would it be any different here? When we set up our angularity, we set the nominal value, which will be the basic dimension. The basic dimension will have a rectangle around it on the blueprint. So you won't actually show that, or it won't actually show up on the print at all. That's very interesting. It's like, well, what's the difference between angularity and angle? Well, let's go back and just output the angle in between this plane and this plane as an angle. Let's go size, angle, and, well, actually, it's probably easier to do this directly. Let's just go grab plane number 4. And one of these, A1XZ, is going to give us the number that we want. In this case, it's minus 40. We could toggle around with this and this, or change the order of measuring to get that to come in as a positive. But for right now, I'm just going to do that, and I'll say plus or minus a half a degree. And I'll say OK, and that gets outputted to our characteristics menu. And notice that right off the bat, the projection angle of that, let's go view and multiple report. We already had all of the measurements that we needed there. So now we have angularity and angle. And notice that our projection angle does have a nominal value of minus 40. That's because an angle is an angular output with an angle format. GDT angularity is you establish where the theoretical plane should be, and then you're working in thousandths of an inch from there, right? So this is a degree format. You got plus or minus. Well, that's funny. I put in a plus and a plus. That's why it's giving us red here. This really should be a minus. But here I have plus 3 thousandths minus nothing. Either I'm at the perfect angle, so I'm 0, or I'm either above or below that, so I'm 3 thousandths, right? Here, I'm either at the perfect angle, which would be nominal value of 40 degrees, or I'm plus or minus half a degree. So really important to notice the difference between angle and angularity. One is a regular degree dimension. The other one establishes a theoretical perfect location or angle, and then you work in thousandths of an inch from there. And the same goes for perpendicularity and parallelism. Remember, both of those are just angularity with predefined nominal values of 0 or 90 degrees, respectively. So, thank you for watching. Hope you learned something. I'll see you at the next video.